Okay, in this video I want to talk about a very important formula called Euler's formula. It's a little famous, you may have seen it before. Something like e to the I pi plus 1 equals 0 or something like that. So we're going to prove this result here in this video, and we're going to really see why it's such a significant result. It's more than just a pretty result. It's actually something very important for complex analysis. Before we do, I want to go back and remind you of some basic calculus things. So remember, the derivative of a function is the slope of the best linear approximation. That's the name of the game with these derivatives. You have some function here in gray, f of x, and you pick a point a on the x-axis. You look at the point above it. So just to be clear, that actual point is, the x-coordinate is a, the y-coordinate is f of a because it lies on the graph. And you want to draw this kind of tangent line, this best linear approximation to the function, right? That line does a good job approximating that function, at least as long as you don't veer away from the point A too far. And the equation of the line is, well, the slope is the derivative, and if you work out what the y-intercept should be and all the rest, you should have done this in like Calculus 1 class. The equation of the line should be y equals f prime of a times x minus a in parentheses plus f of a. So that gives you the height all around. Okay, so if that's the first derivative, what's the second derivative? Well, you know, it's nice to have a best linear approximation, at least locally in a neighborhood of a point, but maybe if we had a best quadratic approximation, then that would be even more precise, right? I mean, a quadratic approximation, you could imagine, would be able to capture at least some of the curving that we see in this gray graph. So the second derivative is necessary for that. The best quadratic approximation is given by this formula. This is like Taylor's theorem or something. F double prime of a times x minus a squared plus over 2 factorial. And remember that factorial, n factorial for n an integer just means n times n minus 1 times n minus 2 all the way down to 1. It's just the product of all numbers from 1 all the way up to n. So this would be 2 times 1, it would just be 2. But there's a reason I'm putting factorial there. But it's given by this formula, and one thing to notice is that the linear part of it, if you ignore this second order term here, if you ignore that for a second, you look at just these lower order terms, that's exactly the equation that we have right there for the best linear approximation. So the best quadratic approximation, one of the very nice things about it is that you get it from the best linear approximation by just adding on a highest order term. Okay, so that's our best linear approximation over there. So then you can continue playing this game. You can say, well, best quadratic approximation is nice. Maybe I could do even better if I allowed a cubic approximation. And then the equation there would be f triple prime of a times x minus a cubed all over 3 factorial plus, and it's just all of this. So the second, first, and 0th order terms come from the best quadratic approximation, and that's the name of the game. We just keep adding a higher order term, and it's always going to be of the form the nth derivative of the function f at a times x minus a to the nth power all over n factorial for all values of n. You can keep going as much as you want. So in the best of possibilities, or the best situation, you can kind of keep doing this infinitely, many times, and the best kind of infinite polynomial approximation, what we call a power series, an infinite polynomial is a power series, will actually converge to the function. It'll be a good approximation to the function, and it'll in fact actually equal the function in a neighborhood of this point, around this point. So that's the whole business of power series, if you recall. So I've written it right here. F of x is equal to, so ideally you'll be able to express the value of a function at the point x by f of a plus 1 over 1 factorial. Well, you know, 1 factorial is just 1, so that's just 1, so it doesn't match it, but 1 over 2 factorial f double prime of a, and so I've already shown it to you before, so this is how it all looks written out. And it's just an infinite sum that continues on and on and on. And if you want to write it as an infinite sum in this notation, it ends up looking like this. So this is a formula you should definitely remember from something like Calculus 2 or something. But an important point to keep in mind is that not every function has a power series. For one thing, it may not have enough derivatives. There are functions out there, and we'll discuss this a little bit later on, but there are functions out there that don't have, that maybe have 4 derivatives but don't have 5 derivatives, or something like this. Once you take the derivative a certain number of times, it ceases to be differentiable. And by the way, even if it does have, for a given function, even if it does have as many derivatives as you need, which I guess you need infinitely many derivatives, right? You just keep going off to infinity. Even if you have infinitely many derivatives, writing down this power series may not give you the function that you started with. But that's not a question I'm going to really address here because it's more of a real analysis question. But a function where you can define the power series and it does equal the function is called a real analytic function. Okay, so that's more of a topic in there. And here a can be anything, right? It was just the point on the x-axis that we decided to do everything around. We could have picked any other point a here, and we could have gotten another linear approximation and all the rest of it. So the choice of a doesn't matter. A equals 0 simplifies things nicely, and a power series at, surrounding a equals 0 is what's typically called a Maclaurin series. So that's just a review of calculus. We're going to continue on. Let's see how we cook up a power series for the function e to the x. So f of x is equal to e to the x. F prime of x, let me switch degree here. F prime of x, the derivative of e to the x, is just e to the x. And so is the double derivative, and so is the nth derivative in general, e to the x. For a equals 0, so if we wanted to do a Maclaurin series, we're going to have to evaluate all of these things at 0. E to the 0 is 1, right? F prime of 0 is e of x evaluated at 0. Well, that's 1 again. It's the same thing. And again, the double derivative is e to the x. They're all the same thing. You evaluate e to the 0, it's always going to give you 1 every single time. So if you write down what the power series for this is, it's going to look like, well, f of 0 is 1 plus the derivative at 0 is 1 times x minus a. But a equals 0, so x minus a is 0. So let me write down what I'm writing, and then I'll simplify it. It's 1 plus f prime of 0 is 1 times, so now we're looking up here, x minus a, x minus a, but a is 0, so this is x minus 0, plus the double derivative now is 1, but there's also a 1 over 2 factorial here, times f double prime of 0 is 1, that's this term, times x minus a squared, again a is 0, and that takes care of that term, and so on. So just simplifying this out, ignoring these 1s that I'm multiplying by, eliminating the 0, just cleaning it up, this ends up looking like 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. It's just x to the n over n factorial. So I'll write it down. So it's the sum as n runs from 0 to infinity of x to the n over n factorial. And 0 factorial is defined to be 1, and x to the 0 is of course 1, so that takes care of my first term here. So that's the power series for e to the x, and yes, it does converge to the function e to the x. E to the x is an example of a very nice real analytic function, so we don't have to worry about that issue. So now let's try this first sine of x. Now sine of x, its derivative is, well, cosine of x, right? Then if you take the derivative again, you get sine of x again, but you get a minus sign. So it's minus sine of x. Then you take the derivative again, you get minus cosine of x. And in general, f to the n of x, the nth derivative, actually depends on whether n is even or odd. And in fact, it depends on more than just that. It depends on whether n is congruent to 0, 1, 2, or 3 modulo 4. What the remainder is when you divide by 4. So I'm going to kind of leave this blank for now. But we all know it's going to either be sine, cosine, negative sine, or negative cosine. It's one of those options, depending on n. When you plug in a equals 0, well, sine of 0 is 0, right? I mean, let's not forget how we calculate things in this trigonometry, sine of 0, cosine 0, and so on. So recall that when you draw your little unit circle here, you want to plug in the angle theta. You draw this little line with an angle theta between that and the positive real axis, and you look at the point where it intersects the circle. The y-coordinate of that point is the sine of this angle. The x-coordinate is the cosine. So sine of 0 and cosine of 0, that would be when theta is equal to 0, which would mean that it would actually be right here, this horizontal line along there. So of course the x-coordinate of this point at the far right end of the circle is 1, and the y-coordinate is 0. So sine is y-coordinate, it's 1, and it's 0, and cosine is 1. Okay, so just reminding you of that. Okay, so sine of 0 is equal to 0. Cosine of 0 is equal to 1. Negative sine of 0 is equal to 0. And then if I had the third derivative here, that would be negative cosine, and it would be negative 1. So what is f to the n of 0? Well, it switches between 0, 1, 0, negative 1, etc., etc., etc. So if you write it all out, what does this look like? Expanding it in the same way we explained this, you do f of 0 is 0, plus f prime of 0 is 1, times x minus a, but x minus, if a is 0, that's just, again, like up here, that's just going to give you x, so that's just 1 times x. So I'm just going to write it as 0 plus x, and I'm even going to drop the 0, I'm just going to write the relevant terms. So anytime we have a 0, the coefficient is 0, it's going to go away. So we can ignore this, because these things are 0. And so it's just going to be x. And then the next term is the odd term, the cubic term. So that would be the triple derivative, which we said was negative 1. So that would be minus. And it would be 1 over 3 factorial. We're on the third term. And it's just a minus 1. And it would be times x cubed. And then the next non-zero term, you skip the fourth term. All the even ones are going to give you sine terms, which when you evaluate at 0 will give you 0. So we're just really doing the odd terms. The next one will be a plus 1, because it'll be a positive cosine, and that will be 1 over 5 factorial, x to the 5th. And then you'd subtract 1 over 7 factorial, x to the 7th, and so on and so forth. Alright, so that's the power series for sine. You can, for yourself, write it with this nice sigma notation if you like, or look it up in a book. But let's quickly move on to cosine. So the derivative of cosine is negative sine. The double derivative is it would be negative cosine, and then so on and so forth. When you evaluate cosine at 0, you get a 1. Sine at 0 gives you 0. Negative cosine gives you negative 1. So it's a very similar picture, except everything's kind of off by 1. These instead of the even terms vanishing, it's the odd terms that vanish. So here we get our 0th term, f of 0, that's 1, plus, well, this term is 0, so we can ignore it because of this. Then we get actually a minus 1, so that's minus times 1 over 2 factorial x squared, and then the next term, the cubic term, will vanish, and then it'll be plus 1 over 4 factorial x to the 4th, minus 1 over 6 factorial x to the 6th, and so on. So that continues on in this way. Okay, so now we've got the formula here, the power series formula for the exponential function. It looks like this. And we've got the sine, and we've got the cosine. It's given by this formula. So now let's ask an interesting question. What is e to the ix? And let's pretend for now that this is legal. I know it looks really weird at first. The exponential function is a function which takes real numbers to real numbers. You have no idea what it means to put an imaginary number into it. You know, what in God's name does an imaginary exponent even mean? But just pretend for now that this is perfectly legitimate and legal, and we're just going to see what it looks like if we plug it into the power series. Alright, so let me switch to black here. So that's all we're going to do. We're going to plug this into the power series. E to the ix. So we're just going to go to what e to the x is. This is actually equal to e to the x. That's the whole point of it. This power series is supposed to equal your function value at f. So e to the ix is equal to, well, we're just going to replace the x in our power series with ix. So it's equal to 1 plus, instead of x, we're going to write ix, plus, instead of x squared over 2 factorial, we're going to write ix squared over 2 factorial, plus ix cubed over 3 factorial, plus dot dot dot. So now we can simplify this a little, because remember, I squared is equal to negative 1, I cubed is equal to negative 1 times I, which is negative I to the 4th is equal to 1, I to the 5th, we're back to I to the 6th, we're back to negative 1, etc., etc. So we have a 1 here, that's just a regular old 1, and I'm going to start writing in alternating colors here. So we have ix, right there, and then we have this ix squared term. Well, I squared is equal to negative 1, so that's actually just negative x squared over 2 factorial. Back to red. Now we're I cubed times x cubed, but that's negative I, so that's minus I times x cubed over 3 factorial. That's simplifying that term. And if you continued on, I didn't write that term here, but the next term would be I to the 4th, which would be 1, so it would just be plus x to the 4th over 4 factorial. Now there's a reason I've been alternating these colors here, because if you pay attention to the black only, so we're just going to rearrange the sum a little bit here, and we'll pretend that that's perfectly legal too. It's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and it's clear all the even terms will have no I, they'll be in black, so it'll be minus x to the 6th and so on and so forth. And we're adding that to, what? Well, notice that the red terms all have a factor of I in front of them. And if you look at the next I term, the next red term, it would be plus I x to the 5th over 5 factorial. Alright, so we can factor out all of the i's, and I'm going to do that right from the get-go. Plus I times, and then all we're left with is a negative x cubed over 3 factorial, and a positive x to the 5th over 5 factorial, etc., etc., etc. So that'll be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and it just continues on with the 7th order terms and so on. So all I did is I looked at the power series for e to the x, and I just plugged in an ix. That's all I'm doing, and I'm simplifying it a little bit. But now you'll notice something. This was the formula we got for the power series of cosine, and that matches up perfectly with this. And x minus x cubed over 3 factorial plus x to the 5th over 5 factorial is exactly the power series we got for sine. So we can simplify this. We can say e to the ix is actually equal to, as we've seen, this thing is actually equal to cosine of x. And this thing over here is equal to, well, we are multiplying by I and adding, but aside from that, what's in the parentheses here is equal to sine of x. And so we've just proven a very powerful and important formula here. Choose blue. E to the ix is actually equal to cosine of x plus I times the sine of x. And there are some fun things we're going to see you can do with this formula in the future. But just some easy stuff right now. First of all, I can prove that original formula I quoted for you. E to the I pi is equal to, well, cosine of pi plus I sine of pi. Let's go back up to our little circle here. Pi is 180 degrees, which puts us over here. So it looks like cosine of pi is going to equal -1. It's the x coordinate, and sine of pi is equal to 0. So this is going to equal -1 plus 0 times I. It's just going to equal -1. So e to the I pi equals -1, or adding 1 to both sides, e to the I pi plus 1 equals 0. So it's just applying this more general formula to the specific case where x is equal to pi. So that's a cute little application because you have e, I, pi, 1, 0 there. Nice and pretty. But I'm going to mention right now a far more important consequence of this theorem, and really the reason it's so crucial to understand this formula when you're studying complex analysis. It completely alters the way that you understand how to model complex numbers and how to work with them algebraically. So let's see what this actually is. So we're used to, here's the nice thing about it, e to the ix, this is our real part, and remember that that's always the x-coordinate when we plot it on the plane, the complex plane, and this I times sine x, so sine is going to be the imaginary part. And remember that's always plotted as the y-coordinate. So y-axis is the imaginary axis. So that means that when we look at how things should be in the complex numbers, there's our imaginary axis, our real axis, you're using an x-coordinate of cos theta, a y-coordinate of sine theta, or I sine theta if we're thinking of this as being in the complex plane. When you add them together, you get e to the I theta. But cosine theta, comma sine theta, well, that's exactly the picture, the x and y coordinate that we had up here when we were talking about these circles, right? It's exactly the same picture here as down here in the complex plane. So what we're describing is the unit circle. Or if you're not convinced that cos and sine, or you don't remember why, well, cos squared of theta, you square the x-coordinate, plus you square the y-coordinate, sine squared of theta is always equal to 1, right? So that's how you know that this radius is always equal to 1. So the moral of the story here is that e to the I theta is always a point on the unit circle. Euler's formula gives us its x and y coordinates, its real and imaginary components. And those are cos and sine theta. And that forces it to be on the unit circle. But not only is it a point on the unit circle, what's the angle here? Well, cos theta, sine theta, again, it matches perfectly with the picture we had up there. It's a point on the unit circle at angle theta from the positive real axis, from the positive x-axis, or the positive real axis, since we're in the complex plane. So that's actually an amazing thing. If you're considering just the function, e to the I theta, and you start off at 0, e to the I 0 should put you right there. E to the I times 0 should put you at 1, which makes sense, because I times 0 is 0, e to the 0 should equal 1. So it puts you at 1 here, 1 plus 0i, there's no imaginary component. And as you let theta increase, what's happening is you traverse the unit circle as theta gets bigger and bigger and bigger. And indeed, when theta hits 2 pi, you end up right back where you started. E to the I times 2 pi is equal to e to the I times 0 is equal to 1. And then it just continues again and again. You're going counterclockwise. And you can see visually now the theorem we just proved, why e to the I pi is equal to -1. Because you start off at 0, pi is 180 degrees, so e to the I pi puts you right there on the unit circle, which is actually on the real axis, and in fact it's equal to -1. Right? -1 plus 0i, there's no imaginary component there. So e to the I theta, this remark right here is probably really the whole point of this entire video, and is the most important point that you should walk away with. E to the I theta is a point on the unit circle, and it's an angle of theta. Okay? So now this gives rise to a nice polar coordinates for complex numbers. Because what you can do is you can say, all right, let me just draw a quick sketch right here. Suppose I have some complex number right there, and I'm drawing it kind of as a vector to that point. What you can do is you can say, all right, there's my unit circle. let me first figure out what the angle I need is. There's my theta. And I know that this point here on the unit circle is given by e to the I theta. Okay, that's what we have here. It's this picture over here. But then my point isn't on the unit circle. Maybe it has a length that's longer. Okay, but if the length of this is r, what we have here is essentially a unit vector pointing in the same direction as the vector we want. All we have to do is multiply by the scalar that's the length. So this point is e to the I theta. This point is e to the I theta scaled by a factor of r. R e to the I theta. So you're rotating, you're going here and figuring out the angle first, and then you're stretching it so that it has the right length. So the complex number z has length, or modulus, r, and it's at an angle, or argument, theta from the positive real axis, then that forces z to equal, well, for it to have the right angle, it had better be e to the I theta, but then for it to have the right length, we had better multiply it by r. So z had better equal r e to the I theta. Or to see this using Euler's formula more directly, if we think of z as equal to x plus yi, where this is the real part of z and this is the imaginary part of z, right? The x and y coordinates. Well, this is actually equal to r cos theta and r sine theta. So remember the way that we move between Cartesian coordinates and polar coordinates in general. Let's draw it one more time. So there's my x and there's my y right there. Or there's my y and there's my x rather. So there's y, there's x, the length here is r, and the angle here is theta. And just by simple trigonometry here, the cosine of theta is x over r, or rather x is equal to r times cosine of theta. And similarly the sine would be y over r, so that y would equal r sine theta. So that's just thinking of r and theta in terms of the polar coordinates. So x would have to be r cos theta, y would be r sine theta. Since z is equal to x plus yi, that would be r cos theta plus r sine theta times I. But you can factor out an r, and it would be r times cos theta plus sine theta times I. But by Euler's formula, that is precisely equal to e to the I theta. So the whole thing is equal to r e to the I theta, and we obtain that formula in another way. So again, the e to the I theta determines a point on the unit circle with the same angle as our complex number z, and then r scales it so that it's at the correct length. So this is really the whole importance of Euler's formula. It allows us to think of polar coordinates for the complex numbers. Now, I was a little fishy about what do I mean by e to the I theta. I kind of gave you a power series for it. Hopefully I've convinced you of it. Right now you don't have to worry too much about it. Just think of this as kind of more of a notation than anything else, telling us what the length and the angle is, almost as polar coordinates. And it does obey some of the nice properties. But I promise later on when we talk about things like analytic continuation and power series and complex power series and so forth, we'll be able to understand what e to the I theta means in a more rigorous way, and it'll fit nice and pretty with the version of things that we saw here using power series.